All right, so we're going to talk about ellipses now. And remember, ellipses are another conic section, and you can see that right here. Here is a cone, and if you slice the cone so that the slice is not parallel to one of the sides of the cone, is not parallel to the base of the cone, and is not perpendicular to the cone, to the base of the cone, you get an ellipse. So it's going to make this kind of stretched out circle. So what we're going to do is we're going to talk about what the definition, the formal definition of ellipses. We're going to look at how to derive the formula, and we're going to look at the parts of the ellipse and key vocabulary. So really this video is just kind of the introduction to the ellipse. So here's the definition. An ellipse is a set of all points such that the sum of the distances between any point on the ellipse and two distinct fixed points, called the foci, is constant. So what does this mean? Well, let's take a look at a little GIF, and I'll explain what's going on in the GIF. But remember, the key is, if you take a point on the ellipse and you measure the distance to two fixed points, the sum of those distances will always be the same. Okay, so let's look at a GIF. Okay, before we look at an animation, here's an image to kind of show what's going on. So the red dotted line represents the ellipse. And then here's a pencil right here. These two fixed points right there are called the foci. Foci, by the way, is plural for focus. When I'm writing things down, you'll see what I'm talking about there. But so we have a focus here and we have a focus here. They're fixed points. They're not going to move. And imagine a piece of string. This blue represents a piece of string. So if you stick your pencil inside the string and just trace along, pulling tight on the string, the length of the string won't change. So this individual distance may change, and this individual distance may change, but the sum of the distances is the fixed length of the string, and that won't change, and that's what's going to create this shape, which is called an ellipse. And so then you can see that's what we have going on here in this image. The two blue thumbtacks represent the two foci, and we can see the string that's wrapped in between them, and you just draw your pencil around and it makes an ellipse. But again, the string isn't changing length, so the sum of the distances to the two foci is remaining constant. And there you go. There's an ellipse. Okay, so here we have an ellipse, and you can see that we have these two fixed points that I put there. So according to the definition of an ellipse, if I take any point P on the ellipse and I measure the distance from that point P to one of the foci, and I add the distance to the other focus, then that distance, the sum of the distances should always be constant. And that's the definition. We're going to use that definition to help us derive a formula. So let's go ahead and label some stuff here. One thing that's by convention, the distance from the center to one of the foci is always, that's constant because these are two fixed points, and that distance is going to be C. We always represent C with that distance. So that means I now know the coordinates. The coordinates for this point are negative C0, and this point is C0. And we'll just call this F1 and F2 for focus 1 and focus 2. Another thing, in this one, there's two conventions, and so I'll tell you which one we're going to use. One convention, this is the one we're not going to use. One convention is to define whatever the furthest distance is from the center to the ellipse as A. Right now we have a horizontal ellipse, but I could rotate this picture and have a vertical ellipse, and now A would be measured vertically. So A is always the biggest distance, and then B is the shortest distance. That's not the convention we're going to use, though. What we're going to use is that A is always the horizontal distance, and B is always the vertical distance. And I think it's just easier to keep track of everything when we get into the formulas. So that's what we're going to use. It doesn't matter. I mean, in the end, you get the same result. So if A is always the horizontal distance, then this point right here, and actually I'm going to just call this point M. That's at A0. I'm going to call this point up here on the y-axis N, and this is at 0B. That means this point right here is negative A0, and then this point right here 0, negative b. So there we go. There's a whole bunch of stuff here. Now I'm going to be defining some points and stuff later, but for now we're just going to use n, m, and p. So according to the definition of an ellipse, this means that the distance, any point, and p is any point on the ellipse, if I measure the point from p to f1 and I add p to f2, that should be constant. And that's the definition we're going to use to help us derive the formula. However, I don't know what that constant is. What is the constant? Can't really do much with this formula yet until I figure out what constant to put there. So let's take a break from this and see if we can figure out the constant, and maybe we'll find some other relationships out here too. So going back to the picture of an ellipse, M is a point on the ellipse. So again, the distance from M to F1 plus M to F2 should be equal to this constant, and N to F1 plus N to F2 should also be equal to this constant. So I'm actually going to make a formula out of that. I'm going to say that N F1 plus N F2 should equal M F1 plus M F2. All right, let's see what we can do with that. So the first thing, let's look at the N to F1. So N to F1, that's this distance right there. Well, look at what we got here. We have a right triangle. So I can easily find the hypotenuse of the right triangle by just doing the Pythagorean theorem. Leg squared plus leg squared equals the hypotenuse squared. I know this leg is C, and I know this leg is B, so C squared plus B squared equals the distance squared. And so that's what I'm going to use. I'm going to get rid of this triangle on the picture though. So C squared plus B squared would equal the distance squared, so I just have to take the square root and I get the distance. And then I'll do the same thing over here for N to F2. I have another right triangle. But look, it's the same right triangle. I have this distance right here, which is C. I have this one, which is B, so C squared plus B squared equals the distance squared. Again. So I can go ahead and just put that down again. So now I know N to F1 is this root, N to F2 is that root. Now let's find M to F1. So M to F1, well, if I just go to the center first, M to the center is A, and then the center to this focus is C. So that is just A plus C. And then for M to F2, that's just this little distance right here. So if I take A and then subtract off C, it gives me this little bit right here. So A minus C is that. So now I have a formula right here. Let's just go ahead and see what happens, what I can get out of this. So I can combine those roots since they're the same and say 2 times the square root of C squared plus B squared. And then over on the right hand side, the C's cancel out. So I have 2A. And then I can also, if I just play around with this thing, first of all, divide everything by 2. I get the square root of C squared plus B squared equals A, and then square both sides, I get C squared plus B squared equals A squared. So there's a couple of things that actually this gives us. Number one, remember I was looking at the distance. I wanted to know what the sum of the two distances would be. I have that right here. The sum of the two distances, I could say it's 2 times the square root of C squared plus B squared. It's kind of ugly though. But I could also say the sum of the two distances is 2A. That tells me what my constant is. I'm going to make a note of that. This constant is 2A. That was found because of this and this and this gives us 2A right there. So that's going to give us something to derive the formula, but it also gives us this equation right here, which when we go to solving problems, this is a nice relationship, that C squared plus B squared equals A squared. So All right, so now we're going to go ahead and derive the formula. I'm going to go ahead and just move this down a little bit. I'm going to need a little bit of room. Okay. All right, so let's see what we got here. So now we know that PF1 plus PF2 has to be that constant distance, which is 2a. So let's come up with something that represents PF1 and PF2. And of course, that's going to be the distance formula. So this point P represents any point on the ellipse. I don't know where it is. All I can do is label it as xy. But now I'm just going to use the distance formula where it's the square root of x1 minus x2 squared plus y1 minus y2 squared, and so on and so on. So the distance between P to F1 is the square root of x minus negative c squared plus y minus 0 squared. And then the distance from P to F2 is x minus c squared plus y minus 0 squared, all under a square root. And we know that that equals 2a. And, I mean, theoretically, well, actually not theoretically, actually we have the equation of the ellipse right there. That is a rather complicated version of the ellipse. You're going to see that we can actually simplify it down a lot nicer than that. So the first thing I'm going to do is I want to try to get rid of these radicals. And unfortunately, I can't do what I did over here and just combine them because they're not exactly the same. This is a plus sign and that's a minus sign. And doggone it, it makes them different and I can't combine them. So what I'm going to do, the easiest way to do this is actually going to be to separate them first. So I'm going to go ahead and subtract one of them. Doesn't matter which one. So I'll subtract the second one. And move it to the other side. Okay, so we have that. Now I can square both sides. And so this right here, when I square it, actually here, I'll show it. I'm just going to square this, and I'm going to square this. And so this right here, it's going to cancel out with the radical. That side's easy. So I have x plus c squared plus y squared. But over here, not so easy, because I essentially have a binomial. So I have to FOIL this whole thing out. I have this minus this. So after you FOIL it all out, you're going to have 4a squared minus 4a times the square root. And then plus the square root squared, but that's going to cancel out the radical. And we'll have this. Oh my god, I just made it worse. But we can see that some stuff will go ahead and cancel out. One thing right away is there's a y squared on both sides. Just cancel that out. The next thing I'm going to do is I'm going to go ahead and square out this. I'm going to square this, and we'll see some other stuff will cancel out. So I'm going to have x squared plus 2xc plus c squared. And then I have equals 4a squared minus 4a times the square root of x minus c squared plus y squared. And then I square the x minus c. So I have x squared, minus 2xc plus c squared. So now there's an x squared on both sides that'll cancel. There's a c squared on both sides that'll cancel. Oops. And this 2xc and this minus 2xc, if I go ahead and add this over here, it's going to make 4xc equals 4a squared minus 4a times the square root of x minus c squared plus y squared. All right, that's looking a little better. In fact, there's a 4 in every term. Well, let's go ahead and divide by 4. So xc is a squared minus a times the square root of x minus c squared plus y squared. All right. Well, it looks better than what we had, but we can do even better than this. Doggone it. I still have a radical. I want to get rid of the radical. So it's going to be easiest now if I go ahead and isolate the term with the radical and then square both sides again. So I'm going to go ahead and add the radical to both sides just to make it positive. I don't know why. Just because. And then I'll subtract the xc. So I have that. So I've moved this term to the left and made it positive, and I've moved this term to the right and made it negative. But now I can square both sides, and that will remove the radical. So I have a squared, and then I square the radical, and that's all gone. So I have x minus c squared plus y squared. But remember, the a was being multiplied by the entire radical, so the a squared has to be multiplied by the entire radicand, the thing inside. And then over here I have to square this. So that's going to equal a to the fourth minus 2 x a squared c plus x squared c squared. Well, I guess the good news is I don't have a radical anymore, but boy, this sure looks messy. All right, so I'm going to clean it up a little bit. One thing I can do is, there's almost an a squared in every term, but not this one. Let's just divide everything anyway. I'll make a fraction, but that's okay. So I'm going to have x minus c squared plus y squared equals a squared minus 2xc plus x squared c squared over a squared. So I just divided every term by a squared. That cancels this out, so I'm just left with the part that was in the brackets. Divide that by a squared, divide this term by a squared, that goes away, and then divide this by a squared. All right, well, let's go ahead and see what we can do. I'm going to go ahead and square this thing. So we're going to have x squared minus 2xc plus c squared plus y squared equals a squared minus 2xc plus x squared c squared over a squared. Well, there is a minus 2xc that can cancel out. And then I have x squared plus c squared plus y squared equals a squared plus x squared c squared over a squared. Okay, well, now I do have c's in there. Let's see what happens if I actually get rid of the c's. Remember this formula up here? If I were to rewrite that and say that c squared is equal to a squared minus b squared, I can replace these c squareds with a squared minus b squared. Let's just see where that gets us. All right, so there's enough. So the c squareds in here are going to turn into a squared minus b squared. So I have x squared plus, and then it'd be c squared, so I'm going to write a squared minus b squared plus y squared equals a squared plus x squared, and then times the quantity a squared minus b squared all over a squared. Well, all right, I'm not sure where you're going with this, Miss Showing Hair, but we're going to go with you. There is an a squared on both sides. That's going to cancel out. So that's good. And then let's take a look at what we'll have left. I'm going to have left over here, I'm going to go ahead and split this fraction up. So on this side, I have x squared minus b squared plus y squared. And on this side, I'm going to have x squared times a squared, but it's over a squared. So the a squareds will cancel out, and I just have x squared. And then I'll have x squared times b squared over a squared, and nothing cancels out there. Okay, well, there is an a squared on both sides now, and that will cancel. This is getting better, and I'm almost there. So I will have negative b squared plus y squared equals negative x squared b squared over a squared. All right, well, let's see what we can do with that. So I'm going to go ahead and arrange some terms first of all. I'm going to move this term to the left to make it positive. I'm going to move this term to the right to make it positive. So I'm going to have x squared b squared over a squared plus y squared equals b squared. And then I'm almost done. I have one more step. If I divide every single term by b squared, divide this term by b squared, it's going to cancel out. Divide this term by b squared. And then if I divide this term by b squared, I get 1. Whew! And that's it. That's a much nicer formula, and that's our standard form for an ellipse. Okay. So now let's go ahead and just look at some parts of an ellipse, but I'm going to summarize this more on the next video. All right, so here we have a summary of everything that we just did. So you can see we have a horizontal ellipse right here, and a horizontal ellipse is going to be stretched horizontally, and notice that the two foci are also arranged horizontally. If we have a vertical ellipse, it's stretched vertically, and the two foci are arranged vertically. So both of these have a formula though, the same formula, x squared over a squared plus y squared over b squared equals 1. Because these points right here, the horizontal points, they're always going to be a0. It doesn't matter if a is shorter or longer than b. And then these points vertically, 0b, and this one's at 0b. So if it's going to be a horizontal ellipse, you can see that a is going to be longer than b. So this a is greater than b. But over here on the vertical ellipse, now a is a smaller one. So a is less than b. So you can always tell by looking at the equation. Look at the denominator of the x squared. If that's bigger than the denominator of y squared, it's going to be stretched along the x-axis, so it's going to be horizontal. If the denominator of y squared is larger, then it's going to be stretched along the y-axis, and it's going to be vertical. So that's easy to tell. The pink points, some definitions. The pink points in these pictures are called the vertices. The vertices are the ones that are the furthest away from the origin. So this will change depending on how it's oriented. If it's a horizontal ellipse, the vertices are along the horizontal axis. If it's a vertical ellipse, then the vertices are going to be along the vertical axis. So the vertices are always the furthest away. And then we have this thing called the major axis. It's kind of like a circle. An ellipse works a lot like a circle, except a circle has a diameter that's always the same. We can't really talk about the diameter here. But we can talk about the furthest distance, and that is the length of the major axis, is what we call it. It's a distance between the vertices. So a horizontal ellipse, the major axis is horizontal. A vertical ellipse, it's going to be vertical. And so on this one, we can see that the length is going to be 2a, but on the vertical ellipse, it's going to be 2b. And then the blue points, those are called the co-vertices. And so that's our minor axis. And the length of the minor axis for a horizontal ellipse is going to be 2b. But for a vertical ellipse, it's going to be 2a. So the minor axis is a shorter distance. Now the other thing is C. Let's not forget C. So remember these points right here. This one is at negative C0. This one's at C0. These guys on the vertical ellipse, now we're going to be at 0C and 0, negative C. So C is the distance from the focus to the center. And if you take a look, The longer distance here is going to be A. A is definitely longer than B. We just defined it. And of course, A is longer than C. So A is the longer one. So when you're thinking of the formula to relate A, B, and C together, since A is the longer one, then you say that the other two add up to that. In other words, where should I put this? I'll put it right here. A squared is B squared plus C squared. Over here on this one, now B is the longest distance. So we're going to say B squared is A squared plus C squared. So just always think about what the longer distance is, and that'll tell you which way to arrange the letters here. All right, so there's the summary of an ellipse centered at the origin.